Okay, this is a worked paper. It's a CIE paper. As you can see on the top here, it's a pure 3 from February 2022. So this is the first part. There's it's a 1 hour 50-minute paper, and whilst it won't take me that long to go through all the questions because I'm going to miss out some of the working. There are probably too many questions for one video, so I'm going to split it into two. This is part A. So let's have a look. Solve the inequality. The absolute value of 2x plus 3 is greater than 3 times the absolute value of x plus 2. Absolute value meaning that if this works out to be a negative, then we take the positive value. So, right, these are a bit of a messy things to do, and there are a number of different ways of doing them. This is the approach that I use, which I notice doesn't correspond to what's given in the mark scheme, but anyway, this is what I like. It's a bit laborious, but it works. Okay, so let's have a look. The idea behind this really is that there at certain value, this x plus 2, let's say here, at x equals minus 2, for values less than that, it's going to be negative, and for values greater than that, it's going to be positive. And we've got a similar thing in here with x equals minus 3 over 2. So those two are the actual critical values in this sort of analysis. So the approach basically is to, well, if we've got two critical values, we've got three critical regions. So we're going to consider the solution in each of those three critical regions. Okay, so consider these two things on the number line. So the first one we're going to look at is the leftmost, x is less than minus 2. Now in that situation, both of these absolute values are going to take the negative value. So what we can do actually is if we replace the absolute value straight lines by brackets, well, I missed them out now, and then take the negative of that. All right, so so our 2x plus 3 becomes absolute 2x plus 3 becomes minus into 2x plus 3, and our absolute x plus 2 becomes minus into x plus 2. Okay, so if we write that out, well, I've dropped the minuses, but what I have done is change the sign around, which is important. If we multiply by a negative number, which is what we're doing in effect, then we must switch the sign. So so that works. If we work that through, that simply comes to x is going to be greater than minus 3. Now that fits, that works, because that is valid for our the interval that we have taken. Since we've got critical value of minus 2, we're only considering from minus 2 below, then that's going to give us a sort of partial solution of x is between minus 3 and minus 2. Okay, so that's that bit. Right, now if we consider this middle region between minus 2 and minus 3 over 2, in this case, then this 2x plus 3 is going to be negative, and x plus 2 is going to be positive. So if we actually replace our vertical bars here by brackets, so this first one's going to be negative, the second one's going to be positive. I've actually multiplied that out as well. So we've got another inequality here, which we can solve, and we take that through, and that's going to give us x is less than minus 9 over 5. So that basically actually kind of trims down our interval between minus 2 and minus 3 over 2. So we've not got quite the width. We're going from minus 2 up to minus 9 over 5. So that is the sort of the second part of the solution. Now, the other one is when x is greater than minus 3 over 2, in which case both of these are going to be positive. So we can replace our absolute value signs by brackets, and we get this 2x plus 3 is greater than 3 into x plus 2, giving us x is less than 3. Now, when we compare this to the range that we've been looking at, we can see that we've got a contradiction here. So this is not this solution is not valid. So we have to jump that, and what we're left with is this solution and this solution, which we can actually glue together. This is x is going to be between -3 and -9/5. So that is basically how we do that. Right, so now this, just to kind of illustrate this, we've got the graphs of the left-hand side function and the right-hand side function. The red being abs 2x plus 3, and this blue being 3 times the abs of x plus 2. And what we're looking for are those bits of the graph where the red line is higher up than the blue line. We can see it's that section there, and that you can probably see that goes between -9/5 there, just a bit less than -2, and -3 there. So that interval there. So that kind of illustrates it. Right. Okay. So that is that one. Let's go on to the next question. So this is a complex number question. On a sketch of an Argand diagram, that's what we're drawing here, shade the region whose points represent complex numbers z satisfying the inequalities z plus 2 minus 3i is less than or equal to 2 modulus of. So this is the length. This value has a length, and the argument of z is less than or equal to 3/4 pi. So just as by way of a sort of a bit of revision, what are the different forms of complex numbers? How do you convert between them? Well, this is just from Wikipedia. Complex numbers have 3 primary forms: the general form, a plus ib, Cartesian form, I think that's called. The polar form, which is r times cos theta plus I sine theta, and the exponential form z equals rx I theta. Right, okay, might hold that thought, and that might be useful when you kind of understanding this. Anyway, what we are looking for here, really, if we rephrase this this modulus here in this form, then what we actually want is we want to draw the area where we can put z so that the distance between the complex number z and this point -2 plus 3i is going to be less than 2. So if we draw a circle center -2, 3i with a radius of 2, then that, including the actual edge as well in this circumstance, because it's less than or equal to, that would define this inequality here. Now the second thing is the argument of z is 3/4 pi, 3 pi by 4. So this is the angle of the complex number. So the complex number is in here. This would be the angle here. What we're looking for is a number which is really within this whole range around here, between 0 and 3 pi by 4. So this line is the other constraint. So if we put those two constraints together, we see that the area that satisfies both of these constraints is this bit here, this larger part of this circle. Okay, so so that is that one. All right, let's have a look at this. So straight line graph, but natural log of x against natural log of y. The variables x and y satisfy the equation x to the power of n plus y squared equals c, where n and c are constants. The graph of natural log y against natural log x is a straight line passing through the points 0.31, 1.21, and 1.060, 0.91. I showed. Find the value of n and the value of c correct to decimal places. Okay, so log graphs are quite useful things, you know, where we've got sort of exponential functions, then we can actually sort of convert this to a straight line graph. And if we take the log of either side of this, we're using the natural log in this situation, but you could do the same log base 10, and often questions do involve using log base 10. Anyway, this is natural log. So what we've got is the natural log of x to the power of n, which is, of course, n natural log of x, log rules, plus natural log of y squared, which is 2 times the natural log of y, equals the natural log of c. Right, okay, so this is a useful form. If we now rearrange this to natural log of y equals this, okay, dividing through by 2, and rearranging half natural log of c minus n over 2 times the natural log of x. Now this is basically a straight line, isn't it? Because this is the this is your kind of your vertical variable is equal to the gradient times the horizontal variable plus some constant. Where have we seen that before? Y equals mx plus c. Yeah, so we can glean from this that actually this minus n over 2 is the gradient, and this, of course, would be the intercept. Right, so where are we getting this from? This minus n over 2. Well, if we do a sort of a bit of a measurement on this and we work out the rise over the run, okay, so the rise is this. It's actually negative, of course, because it's going down to the right, minus 0.3, and the run is this here, 0.75, and that works out to be minus 0.4. So our minus n over 2 is equal to minus 0.4, so therefore n equals 0.8. Right, okay. So, so that's first part. So C. So if we think about this point here, we could use either points, but when we use this one, then going back to our equation up here, the natural log of C is equal to 0.8 times the natural log of x, 0.8 times the natural log of x. So log of x value. Plus 2 times the natural log of y, plus 2 times the natural log of y. All right, well, we can work that through. We get natural log of c is equal to 2.668. And then when we exponentiate both sides, then c is equal to, well, it's e to the power of 2.668, isn't it, which is 14.41. So that is the value of c. So n equals 0.8 and c equals 14.41 are our solutions. Right. Okay, so this is slightly tricky question. That's a parametric equations come trigonometric identity question. Parametric equations of a curve are x equals 1 minus cosine of theta and y equals cosine of theta minus quarter cos 2 theta. Bit of fun actually to get onto Desmos and just put these parameters in and see what the curve looks like. Always good fun. Okay, so we've got to show that dy dx equals this thing here, minus 2 sine squared of a half theta. Right. Interesting. We've got 2 theta here. We've got a half theta here. So, well, the first thing really, if we differentiate each of these parametric equations, we're going to get dx d theta equals sine theta and dy d theta equals this expression here. Now, by the chain rule, we could write this dy dx equals dy d theta times d theta dx. This is a sort of uncancellation, as I sometimes describe it. And d theta and d theta dx is the inverse, is the reciprocal of dx d theta. So actually gluing these two together gives us dy dx is equal to this expression in theta. Now, okay, well, I'm going to try and get away from move towards this from this 2 theta towards a half theta. So the first stage is to move to expand this out, this double angle here, sine 2 theta, which is equal to 2 sine theta cos theta. Well, and then we've got our half to multiply there. So this is going to be sine theta cos theta. So this is what we've got now. And if we divide through by sine theta, we're going to get -1 plus cos theta. Right, that's okay, but we're still not in terms of half theta, are we? But we have a trick up our sleeves, and that is basically to do this. If we kind of separate this out, so cos 2 over half theta, then we can use our double angle formula on this bit. Okay, so cos 2 of a half theta is going to be cos squared half theta minus sine squared half theta, got our -1 there. And then we do a conversion on cos squared half theta, which is equal to 1 minus sine squared over half theta. Okay, so convert that. And we get this minus this minus this, which equals this. Okay, so if you're not convinced, you might want to pause the video and just kind of gaze at that for a bit, or maybe just kind of work it through for yourself. That's how it goes. So that's quite tricky, but a good learning point there. This little trick is sometimes needed. Right, okay, another trig question here. The angles alpha and beta lie between 0 and 180 is such that tan alpha plus beta equals 2 and tan alpha equals 3 tan beta. So simultaneous equations, basically. The only thing, though, is we can't do anything with this unless we can actually separate this out, the alpha from the beta. Fortunately, we've got our tan identities, and this is the one we're going to use, tan alpha plus beta. So if we apply that, let's have a look. That 2 equals, yeah, tan alpha plus beta is equal to this. And then if we deploy this one here and eliminate tan alpha, we're going to have 3 tan beta from there, plus tan beta is equal to 1 minus 3 tan squared beta. Right, okay. And if we, so what we've got is 2 equals this expression. Right. So if we cross multiply, get it all on the numerator line, rearrange it, we get it in the form of quadratic. And so we can just go ahead and solve this quadratic now. If we do that, we get these 2 solutions for tan beta. Okay, so we can unpick that to find the value of beta, and therefore a value of alpha using this. First thing we should note, though, is that tan alpha plus beta equals 2. So that means that alpha plus beta is going to be, well, 63.43, or it could be 243.83, or it could be, keep on adding 180s. But these are the 2 that will do us. So first of all, let's take that first solution, tan beta equals 1/3. Okay, so we take the arctan, and we find that beta is equal to 18.43. That's the one in our range between 0 and 180. And so therefore, using this, basically subtracting it from 63.43, we're going to get alpha is equal to 45 degrees. Right, so that's one pair of solutions. The other pair of solutions comes when we take tan beta equal to -1. And that's going to give us a value of beta equals 135 degrees. We can also -45, but we're not going to be interested in that because that's outside our range. So we're going to take 135. And therefore, alpha will be this because beta and alpha are going to add up to 243.43. So alpha equals 108.43. So those are our two pairs of solutions for this. And if you wanted to check, you could substitute both of those into these and they check out. And similarly, you could substitute both of those in and you will find that these check out. Okay, so that's 5 of them, and we're just going to have a look at this one, which is another complex number question. Find the complex numbers W, satisfy the equation W squared plus 2I W star, which is the conjugate of W, equals 1, such that the real part of complex number is less than or equal to 0. Okay, so this is our Gann diagram here. So this is the real number line, y being the imaginary. So if the real part is less than 0, that means we're looking for solutions over on this side of the y-axis. So, okay. So the way we do these, basically we've got to split it up, let W equals X plus IY. And then if we write out our equation, X plus IY squared plus 2I times X minus IY, because we're using the conjugate, equals 1. We expand all that out, multiplying out, and of course I squared equals minus 1 equals that. Right, we've got a complex number equation here, and that's only going to be true if the real part of the left-hand side equals the real part of the right-hand side, and the imaginary part of the left-hand side equals the imaginary part of the right-hand side. So if we take the real parts first of all, so the real part on the left-hand side is that, the real part on the right-hand side is this 1. So we can factorize that. Sorry, no, this is the imaginary part. We take the imaginary part, then and that's 2x into y plus 1. All right, so look at these two equations. We're looking for a solution. Right, the easiest one to start with is this one, because we can conclude from this that either x is equal to 0 or y is equal to minus 1. So if x is equal to 0, substitute that in here, and we're going to end up with this quadratic equation made up of that y squared, that 2y, and that 1, and that's giving us a value of y equals 1. This factorizes to y minus 1 squared, so y equals 1 is our solution. So so x equals 0, y equals 1. Just looking at the what W is, well, that is just basically W equals I here on the Gann diagram. Now looking at the other solution, y equals minus 1. All right, so if what we do is we substitute y equals minus 1 into the real equation. So x squared minus 2 is what we're getting from that. Minus 1 equals 1. Therefore, x squared equals 4. X equals minus 2. What you might say has happened to the positive solution to this x equals 2. But of course, x is the real part, and the real part has to be less than or equal to 0. So we've only got one solution that we're considering there. And that's going to give us a value of W is, well, x is minus 2, and y is going to be y is minus 1, so minus 2 minus I. So there we go, our two solutions. W is either minus 2 minus I or plus I. Right. Okay, so that is the sort of first half of the paper there, and the other half are going to be in the second video, part B, if you like, of this paper. So thanks for listening.